this actual problem, we're going to be able to use it in the future. So this is, if there's one you're going to pay attention to, this is a good one. This is a good one. Alright, so what we've been doing in class right now, dealing with integrals, and we've come up with situations where it might say, take the integral of, let's say, 6x plus x squared, right? Using integral rules, we know that when there's an addition, we can separate functions, take the integral of each individual, and we can do it for subtraction. But multiplication brings a problem. We don't have any way of taking the integral of two functions multiplied by each other. And our specific problem is trying to take the integral of functions to a negative power. I'll say 1 over a function. And so I'll set this situation up. Let's say you're trying to take the general antiderivative of 1 over f of x, right? But f of x is equal to g of x times h of x. So this is effectively the integral of 1 over g of x times h of x, right? Now, this could be seen in this step as 1 over an entire function, but if you factor it out, you can then separate this into multiple functions, and this is where I'm getting at when I'm talking about multiplication. Because this is effectively 1 over g of x times 1 over h of x. You guys see that? I heard Prince saying that. What this process, partial fraction decomposition, allows us to do is it allows us to go from this step to the step I had on the board earlier where there's addition and subtraction of functions. And so what part A gives us is it sets up a function for us to decompose. And the function is what? Does it say f of x? No. It just says 1 over t times t minus 1 times t plus 1 is equal to a divided by t plus b divided by t minus 1 plus c divided by t plus 1. And what we're going to have to do at this point is we're going to have to find constants for each of these. And you'll see in the end why we do this and how we can even get back to this step. And so Richard's going to come in now and he's going to show you how to actually decompose that guy.
Okay, so let's see.
I don't know if that matters, but you switched it's supposed to
Did
be
I?
t
No.
over t plus 1.
Yeah.
That would be.
It,
Wait, what do you
in terms of our work, yeah, it does. Thank you for catching that. It will matter just because then our constants will be switched up. So that does matter. Thank you very much for catching that. You guys follow so far though?
What does
Then this would be
the
a-
problem saying b over t plus 1?
Yeah. Oh no, wait. No, they weren't switched up.
Yeah,
Yeah,
it's
right.
b over t plus 1.
Yeah.
Oh, okay. I thought you meant on the board it was switched up. Okay. Wait.
Yeah, it's like
Yeah,
that.
you make
Oh,
b
okay,
over
so it's
two
all
plus
set.
one,
Okay.
c over 2 minus 1.
Okay. I get it. Okay. Go ahead.
Okay, so basically we want to get these constants alone so that we can solve for each individually. So the way that we can do that is that we have to get them out of their fractional form. And does anyone know how that we might start by going about doing that? Common denominators. What's one way that in one step we can get all of these to have a common denominator? Multiply what together?
The denominator.
But like which denominator?
All of them.
Exactly. We multiply this whole thing by each's denominator. See, like when we attribute this, or when we distribute this to each step, like the t will multiply out, so it'll get rid of the denominator. You'll be left with this still, but that's okay because you got rid of the denominator, and that's what this will do for each one. So if you distribute, but you know you multiply to this side, so you have to multiply to this side too. So. And as you'll notice here, it's the same here, so they'll cancel out, and this will just equal 1. So 1 equals t's cancel out, so then it's left with t plus 1 and t minus 1 plus b. The t plus 1's cancel out, so you have t and t minus 1. And then the same for c. Okay. So, now we can go about solving for each variable individually. Now, to do that, we're going to substitute in values for t, where if we look at one variable alone separately, if we plug in a certain value, it'll cancel the other two out at the same time. So like if we look at a, we'll notice about these two terms is they both have a t. So if you plug in a 0 for t, then b and c will cancel out and you'll just be left with a. So let's do that. 1 equals a. So these will cancel out, and then 1, this is 1, this is -1, so it's -1, a times -1 is -a, and then they cancel out, and then so if you just multiply by -1, a equals -1. Now if we go through the same process for b, you notice that each has a t plus 1, so if we substitute -1, these two will go away and we'll solve for b, and like the same for this if we substitute in -1, or I mean a +1 for t for these. And so our values come out to equal if we just do that. I'll just tell you. B equals 1/2 and C also equals 1/2.
You guys follow so far?
Yeah.
Get that?
Good.
There you go. And so then we can then go back into the original, which we had said, and substitute in for this. And I'm going to write this off to the side because we're actually going to need to use this later. So 1 over. So a we said was -1, so -1 over t. Then b and c are both 1/2. And that's part A.
Hello.
Nice guy.
Okay, so for part B, it wants us to find this.
Do you want me to erase that for you, Scott?
Oh, that's fine for now, I think.
Did anyone still want to see this to look at it?
Okay. So I want to solve this. We can factor this down and make it factor out x. X is 6 minus 1. And then we can factor that down into 1 over x times x cubed plus 1. Okay. So if you notice this, like, do you see anything familiar about this?
Oh, we should have left it up. Oh no, never mind, it's right there. It's just small.
Yeah, so it's like the same thing as that basically, except the only difference is in that you see you have all the t's are to the same to the same power. So in here you have an x but 2x cubes. So what you can do is multiply the top and the bottom by x squared to make this term x cubed, so that they're all the same. So you would get 1 over x cubed times x cubed plus 1 times x cubed minus 1. So now,
But you wouldn't get that.
what? Oh. Heavy? Okay.
That was
So-
kinda big.
Okay, so you get this, right? And this is similar to what we had before. So now you can do substitution in what could we use as a